Good morning. This is lecture 3 on January, I think it's January 12th today. And I tried to record this lecture in the morning class, but somehow things did not go well. And I mentioned that it's going to get recorded, but with no voice, so basically it's screen capture. However, there is time now that I can devote this, so basically the whole lecture is going to be repeated with audio. Okay. Uh, let's see. The agenda for today is to talk about viscous damping and also damped-free vibration. Okay, so here is a free body diagram of a mass spring and a damper system, and we are assuming that there's no friction between this mass and that surface. Okay, you can also imagine that this is vertically hanging from the ceiling, so basically in that situation there is no surface that it rubs against. The forces that are acting on this mass are shown here. There is a spring force which resists the motion, and there's also the damper force which is resisting the motion of the mass due to the velocity. The magnitude of it depends on velocity. We'll get there in a minute. So dampers are basically one way of making dampers is uh, have a container filled with fluid. Imagine that this is your basic bicycle pump, and there's a container there which is in it is oil, and there's a handle. We try to move the handle. The oil has to go from one side to the other through these holes, and of course that causes the resistance. And your common experience or our common experience is that the faster we try to push the handle, the more resistive force is going to be applied. Okay, so it has something to do with the velocity. That doesn't have to do with the displacement. If you gradually move the handle, yes, there is some force, but not substantial. Now, the common occurrence of these isolated or discrete dampers are in shock absorbers. For example, you can see one here, and there are other applications too, door stoppers, etc. I have redrawn the diagram here for you, the forces acting on the isolated mass, and we use the Newton's second law, the sum of all the forces equal to mass times acceleration. Now notice that both the forces are opposing the motion, therefore they're pointing in the negative direction. So that's why we have negative signs there. And for a viscous damper, linear viscous damper that we're going to consider in this course, the force of the damper is proportional through the damping constant to the velocity of the mass. And the unit of C is basically you stick Newton to the left side and meter per second to the right side, and you clean it up. The unit of C comes out to be Newton second per meter or kilogram per second. I never memorize this thing because it serves no purpose. And if I do, I basically go back to the definition of a linear viscous damper, and excuse me, out of that I extrapolate the unit of C. You remember from your first year class, spring force is equal to stiffness of the spring times the displacement. Okay, and if you put all of these things in this equation, you're going to get the mother of all equations in the vibrations course. And in lecture 2, we assumed there was no damping, so there was no middle term present here. But here we're going to include the linear viscous damping. Now, in your differential equations, prof, or no, well, yeah, differential equation, prof, based on what they have taught you, is that you can write the solution of this as this term, which has a decaying amplitude. The amplitude is not constant anymore. It's multiplied by this thing, and that thing is going to go down as time increases because of the fact that these are all positive. And of course, you have your common sign of omega d plus phi on the right-hand side. Now, when we did this thing in lecture 2, there was no damping, therefore there was no e to the power present here, there was no exponential there, and this omega d was called omega n because there was no damping. Okay. However, back then on Tuesday, we wrote x of t equal to a times sine of omega n times t plus phi. It's nothing new. Now, the values of a and phi depend on the initial conditions. So if your initial condition for x from the displacement from the equilibrium position x naught and the initial velocity is v naught, then a can be calculated according to this formula and phi according to that. Again, these are not new except that we didn't have damping present, so this psi was not there, psi term was not there, and the omega d was actually omega n. They're the same thing. And these are formulas that we gave you on Tuesday. All right. Now, the undamped natural frequency that we discussed on Tuesday was square root of k over m. This psi is called damping ratio. It doesn't have any units, and it's given by that expression c divided by 2m omega n. There are other ways of writing this thing, as you'll see in just a minute. The damped frequency is omega n. The undamped frequency, which we did on Tuesday, square root of 1 minus psi squared. Now, notice that if psi is small, for example, 0.1, this expression becomes almost 0.99. So damping does change the frequency of vibration, but not substantially, unless it's a very unusual situation. Now, this denominator is what is called critical damping constant. So basically, psi is C over C critical. Where C critical, there's two ways to write it. This is one way that is appearing here, but it's also possible to write it as 2 square root of Km. Now, psi is, as I said, C over C critical. So you plug in the value of C critical either from that expression or from this one, and you get the numerical recipe for calculating psi. I'll do an example, but let me, right, let's do this example. Suppose we have a mass and a spring, and there's no damper here. And this is the stuff that we did on Tuesday. Obviously, we know how to handle this problem. The natural frequency is the square root of k over m, and that's it. Now, if you add a damper, we just realized that, first of all, the frequency of oscillation changes, and it's reduced because of the formula for omega d. The question is, what should the value of the damping ratio be so that omega d is 0.9 of omega n, okay? And then there's a second part. We'll do the second part later. Right now, this is very simple. So omega d we want it to be 0.9 of omega n. And there is an expression for omega d, which I write it here. And of course, you plug in for omega d 0.9 omega n. And this is a very simple equation, and you can solve it, and you can get damping ratio equal to 0.436. Okay, 0.436. And for part B says that if the mass is 10 kilogram and the stiffness is 10,000 Newton per meter, what is the value of C? So we have damping ratio, but the question is, what is the value of C? So we go back to the definition of what damping ratio is C over C critical. Now, C critical, this is one way of writing it, but remember, there's also the alternative that the denominator is 2 mass times omega n, which I'm not writing it in that form, not using that form of it. So we just write this thing here. We know psi, and we know m and k, and that's going to give us the value of c. Okay, so that takes care of the example. Now, I want to discuss the role of damping in these in this oscillation. So this psi, the value of psi, which is, by the way, a positive number, will dramatically affect the nature of the oscillation. Now, when I did lecture 2, there was also, lecture 1, sorry, there was also a supplement to lecture 1, a video for that supplement where I considered three different cases, and each one of them correspond to a particular value of psi. Okay, and I showed you that there are three possibilities. You can get a exponential decaying solution, which is overdamped, another exponential decaying solution, also which corresponds to the critically damped, and finally the sinusoidally decaying oscillation, which is the underdamped situation. So each one of these, we want to look at the general context. I don't want to use the specific value of MC and K that I did use in that supplement. The case where psi is between 0 and 1 is called the underdamped situation. And uh, uh, so omega between 0 and 1, for example, something is plotted here, and for a specific value of psi, and the response looks like this. This, unfortunately, is not correct. The value of psi equal to 1 is not 1. Some value, this is a typo on my behalf. When I did cut and paste, I probably took the wrong expression from my source, the textbook. Ignore the psi equal to 1. There is some value of psi, but it's between 0 and 1. It is not equal to 1. This is a bad mistake. Okay, good. So some observations are that, first of all, the motion is oscillatory. You can see that, oscillations, and it's decaying with time. Okay, and the value of the psi will actually tell you how fast this is decaying. If you go back to the solution for x of t, you see that there is, in front of it, there is an e to the power, which is negative of psi and some other stuff. And that negative psi, that dictates the decay rate, okay? And underdamped case, which is something like this, is the most common occurrence in real life situations, but you should be prepared for all three scenarios. When psi is bigger than 1, it's called the overdamped vibration, okay? And the solution looks like that. There is no oscillation involved, and how it behaves can be any one of these three curves. That depends on the value of the initial position and initial velocity. Okay, so here they're plotted for three different cases, and the values are in fact correct now, and psi is this down here. This legend is correct. Okay, but not for the first one that I just showed you, and not for the next one that I'll be showing. So unfortunately, they cut and paste, and it was a bad idea. So yeah, I don't know in the first case and the third case that we're going to discuss what the value of psi are. You can ask me later if you need it. Okay. Motion does not involve any oscillation and returns to rest after uh, the motion always returns to rest position with any oscillation. Okay, we know that, we can see that. Now, psi equal to 1, which is critically damped, again, it depends on the initial conditions. So for three initial conditions taken in these graphs, the value of psi is actually bigger than 1. Sorry, equal to 1. The previous one was, over damped, and psi is a value bigger than 1, okay? So in the previous case, this legend, the value of psi was not correct. Psi was bigger than 1. Here it's okay. All right. So let me backtrack. Psi between 0 and 1, the legend was not correct, which was called underdamped. The next case that I showed you was psi bigger than 1, which was overdamped. And my guess is that, unfortunately, I wrote it as, let's go back here. Now, this is correct, but this is not. Okay, overdamped is correct. And what I'm doing is right now psi equal to 1, and this is, this is correct. Go back one more time. This is not correct. Psi is bigger than 1, and I don't know what the value of psi is because I did the wrong cut and paste. But let's go to the next one. This is fine. This value of psi is equal to 1 is correct. Now notice that again, critically damped, there are different ways of describing it. It's the case where it decays, but the fastest possible way, okay? And there's no oscillatory motion. Another way of saying it, the case that separates non-oscillation from oscillatory response, okay? Because when it was over-damped, there was no oscillation. When it was under-damped, there was oscillation. Critically damped is basically the threshold where no oscillation takes place. And the advantage of doing critically damped is that the decay will go to zero the fastest possible way, okay? But it's not easy to achieve in the real life situation, by the way. All right, so I'm going to say a few words about an alternative way of writing the mother of all equation, which may not be too important for the case of single degree of freedom, but it becomes very important when we do multi-degree of freedom in the last 4 weeks of the course. So here's the mother of all equations. If I divide it by m, we get c over m and k over m. This you recognize, k over m is actually omega n squared. It's right here. And this thing, if you plug in the value of psi, the expression that I gave you for psi, and omega n, you're going to get exactly c over m. So this is the standard form. So notice that the advantage of the standard form is that there are no 3 parameters here. There's only 2 parameters. There is natural frequency and the damping ratio, and these are inherent properties of the system. Because when you look at this, it could become misleading because C, K, and M are all affecting the motion. In reality, there's only 2 things that affect the motion: natural frequency, this is undamped natural frequency, and the damping ratio. Okay? And this is what I just told you. Okay. As far as another way of writing something that I've already presented to you, and what I'm going to show you first is what we already know. So here's our equation. This is the standard form of that equation. This is what you already know. When psi is less than 1, you already know this stuff, and I'm putting it here for your own reference. However, it is possible to look at this expression in a different way. Notice that you have sine of the sum of 2 angles. These are just constant. These things are just constant. But this is sine of sum of 2 angles. Remember from trigonometry, when you have a sine of 2 angles, you can write it as sine of the first one times the cosine of the second plus cosine of the first times the sine. If you do that, you're going to get sine omega d and cosine omega d. And once you plug in the value of a and phi, it all looks like this. So there is the exponential decay term. We know that. It was here. It still stays there. And if you plug in a and phi and use this trig identity that I mentioned, you're going to get a constant times sine of omega d times t, omega dt, plus another constant cosine of omega d. These are saying the same thing. One way of writing it, an alternative way of writing it. And notice that you have to be careful when you use these things. Both omega n and omega d are present. Okay? So some of them are omega n, some of them are omega d, so don't mix them up. Now, there is also a convenient way for the overdamped system. This you already know. Okay, you already know that for the overdamped system. For the case where it's critically damped, psi equal to 1, there is a very easy way of writing it. So when psi is equal to 1, the response of the system is a constant plus another constant times t times exponential decay. And please go ahead to the supplement to lecture 1 and look at the case where you had a situation where the 2 roots of the characteristic equation were identical. I didn't say anything about vibration there. All I did was I gave you 3 different equations. The difference between them were the value of psi, if you calculated it, were one case bigger than 1, another case less than 1, another case equal to 1. The case equal to 1 corresponded to mathematically to the case where the characteristic equation had identical root, two equal root. And if that is the case, your differential equation prof told you that one solution you can write immediately, the second one is just multiply the first one by t, and that's what I've done here. And it's very easy to see why A1 and A2 are these. For example, notice that when you set t equal to 0, you get x naught, right? In the left-hand side of this expression, when you set t equal to 0, you get x naught. And on this side, you get A1, right? Because t equal to 0 makes this go away, you have A1. And if you differentiate this, well, I didn't do that, but if you differentiate this and then set t equal to 0, you're near x dot of 0 is v dot, and you clean it up, you get this expression. Let's do an example. So we have a human leg, and this is in a rigid position, knee lock position. And based on experiment, somebody has done it, and the natural frequency of this bone structure, okay, is, think about it as 20 hertz. Okay, now let's assume that the damping, this is in the longitudinal direction, in this direction. Natural frequency in the longitudinal direction is vibration, longitudinal direction is 20 hertz. Suppose that somebody has assured you that the damping ratio for this structure is 0.224. We're not questioning that right now. You're saying somebody told us this. Well, first of all, we want to know what is the displacement if there is an initial velocity. What is the displacement in the vibration if the initial velocity is 0.6 and initial displacement is 0. So first of all, there is a statement here that imagine that this guy is standing on a table and jumps on the floor. Obviously, we have a mass spring damper system, which is motion. So at time t equal to 0, when it hits the ground, the person hits the ground, we measure x from that position is 0, and the velocity is 0.6. Velocity of the, if you view this thing as a mass, okay, velocity of the mass is 0.6 meter per second. So we are reassured that these are 0.6 makes sense. It's an example. So this would correspond to the vibration induced by landing on your feet with your knees in the lock position from a height. You're not going to use this 18 millimeter here. All it says is an explanation of where you can potentially get this 0.6 meter per second. Okay, and then once we do that, it says what is the maximum acceleration assuming no damping. Okay, this is the damping, but as a part B of the problem, we're going to assume that we want to find the maximum acceleration and there's no damping. Let's not worry about that right now. Well, first of all, 20 hertz corresponds to 20 times 2 pi, 125.6 radians per second. And we're told that the damping ratio is 0.224, and this obviously is between 0 and 1, therefore it's an underdamped case that you're talking about. The relationship between damping, the relationship between damped frequency and natural frequency is given here. So first thing we want to do is we want to find what omega d is, because in the expression for the response, there is an omega d. Remember where I said you have both omega n and omega d present in there? So you need omega d. So 125, this is omega n, and 1 minus damping ratio squared. Notice that even with this relatively high damping ratio, we have a frequency which is not very far from 125. So sometimes people make the assumption that the damped frequency is the same as natural frequency, approximately. Don't make that assumption, please, unless you're specifically asked to do it on the problem. Here is what I said. This is this response of the system. You have omega n in it, you have the damping ratio, and you have the omega d. And of course, phi and a are depending on the initial conditions. Okay, so this is something you have already seen and you're taking it for granted. You can use it. We are told that at time t equal to 0, pretend we are measuring from that kind of equilibrium position, x naught is 0, and initial velocity is 0.6. So in this expression, if you set x naught equal to 0 and v naught equal to 0.6, you're going to get the value of a and phi because everything else you know. And if you do that, you're going to come up with these numbers. Yep. So there's the amplitude, and the phase is right there. If you notice that phase is 0, that's because x naught is 0. X naught is 0, so this whole thing becomes 0, and phi becomes 0. Now, if you plug it in, plug these numbers into that expression that you see on the top, you're going to get the response of the system. So, for example, if you're talking about vibration, if you say, what is the position of the mass once we model that bone structure as a mass spring damper system, what is the position of the mass? Mass, is being representing that entire bone structure. You can plug in the t equal to whatever you're given, and you're going to find the position. So let me also uh, put it this way. Uh, if you're going to model that structure as a mass spring damper system, basically you're saying the two legs together will have the stiffness of K, together will have a damping. These are all in parallel, therefore you add them up, right? So that K that you see in that expression is the two uh, the stiffnesses of the combined two legs. And the damping is the damping of the combined two legs. And the mass that you see is the mass of the person who jumps down. Jumps down. It is not the mass of that two bones. Okay, the mass of the two bones we are ignoring, and you see later in the course how to bring in the effect of mass of the spring and other things. But so I'm just trying to show you, visualize what's going on here. The person has a mass M. The legs have a stiffness together, have a stiffness K. The legs, flesh, and whatever other thing that you have a damping which is C together. Add them up. Okay. So the response of the mass, think about it as the mass center of the person, is given by that expression from the equilibrium position. Equilibrium position means that if you have the person standing on the floor, it has a mass center, the position, it has a mass center, and the displacement from that equilibrium position is what x is. Okay, good. If there is no damping, uh, if there's no damping, obviously omega d and omega n are the same. This is the second part of the question. If there is no damping, first of all, we know that omega d and omega n are the same. And you're told that what is the uh, maximum acceleration? You said what is the maximum acceleration? Okay, maximum acceleration of the body, basically. Okay, so. Well, first of all, we know that the maximum, assuming it's a free vibration, the maximum. Uh, Remember, these are things that we did towards the end of lecture 2. The maximum velocity for a sinusoidal motion is a times omega n. The maximum acceleration is a times omega n squared. The only thing is that we need to know a. So we are told we're given 0.6. We're given 0.6 as V naught, and we calculate omega n. You calculate the amplitude A for, this is for the displacement, okay? It's not the acceleration. This is the amplitude of the displacement. Now, the maximum acceleration or the peak acceleration is A omega n squared. So you take the A that you just got out of that, and you multiply it by omega n squared, work it out, and you're going to get peak acceleration. Okay. I asked somebody in class, or asked people in class, why do we care about maximum acceleration? Remember, maximum acceleration, if you think about it in the naive sense or intuitive sense, if you multiply it by the mass of the block or the mass of the person, will give you maximum force. So mass of the person times the maximum acceleration is going to give you maximum force in a very rough, naive sense. Okay, so if we have that kind of a uh, uh, if you take that and multiply it by the mass of the person, you're going to get the maximum force. If you have the maximum force and you apply it to the bones, that those legs in lock position, then of course you divide it by two because there are two legs there. You can calculate, for example, the stresses in the bone and find out the fracture, etc. Okay, so that's why very frequently people may be interested in maximum velocity, maximum acceleration, and a maximum displacement in case whatever they're thinking has to do with displacement. Okay, but in a biomechanic problem like this, probably maximum acceleration for fracture of the bone is the more uh, reasonable thing that they're looking for. I have also, by the way, plotted this response for you, and it looks like that. Obviously, there's damping, eventually die down. So let me remind you what we're doing. We have a person jumping from a table to the ground. Once it hits the ground, you can imagine the mass of the body, and there's a stiffness for the spring being the legs, and there's damping in the body. This becomes a mass spring damper system. So from the equilibrium position of the center of mass of the body, as if the guy was standing on the ground without any, impact, it was standing, it would have a location for the center of mass, right? That is what we call equilibrium position. And the X that you get is above and below, oscillation above and below that equilibrium position. That's what this is giving you. Let's do another problem. So we have a 10-pound mass suspended. We have the spring, and we know that there's a damper there, but the damping value is so that this is critically damped. We take from the equilibrium position, we take the body and move it down by 2 inches, and we release it. Obviously, the mass is going to go up and down from this equilibrium position, and we are asked to find the value of C. Okay? First of all, find the value of C and then get the displacement at different time. Let's not worry about the second part of it. Let's find the value of C. Okay, first of all, the mass of this object is its weight, which is 10 pounds, divided by G. Now, G is 32.2 feet per second squared, but everything is done in inches, so I'm going to multiply that thing by 12. So it's going to be roughly 360 inch per second squared. So you work it out, you get this number. So this is the unit of this is the unit of the mass when you use inches and pounds a second. I think this is called slinch, if I'm not mistaken. But anyway, doesn't matter. That's what it is. This is the mass. To find the natural frequency, you stick it in that formula K over M. This should never escape you in this course. Okay, K is given right there, and M we just calculated, and we're going to get natural frequency radians per second. Now, we are told that this is a critically damped situation. This is given to us, we're told. So this value of psi is 1. So first of all, the expression for psi is given right here. And these are all saying the same thing. Whichever you want to use. Psi equal to this or psi equal to that, which obviously two equations. So it looks like I'm using this guy. In other words, psi equal to this guy because psi is set equal to 1 on the left side. On the right side, we don't know what C is. And the denominator 2 times the mass, which is right there. And omega I just calculated over there. So I'm using this. And you get the value of C. Okay, then it says, find the displacement after these times. So once I have the value of C, I already know M and K, I can actually write the value of the formula, and this is a critically damped situation. Don't forget that. This is a critically damped situation, so the critically damped situation had this expression. Now, A1 and A2 depend on the initial condition and initial velocity. So this is the initial condition, and this is the initial velocity. And this is not magic. I notice that in this expression, when you set t equal to 0, this A2 term goes away, and you get A1 equal to x of 0, which is x naught. And if you differentiate this and then set t equal to 0, x dot of 0 becomes v dot, and you clean it up, you're going to get the value of A2. Okay? So this is not magic. You just have to do it by brute force. Now we are told that the mass has been moved down by 2 inches and let it release from rest. So v naught is 0, x naught is 2. Just work this out. So that number this number A2 is there, and of course x naught is 2 inches. So plug it in right here, 2 plus this times t exponential. There is no sinusoidal oscillation here. There's no oscillation because, after all, this is a critically damped situation, and you're asked to find the magnitude value of the displacement after 0.01 second, after 0.1 second, and 1 second. And just plug it in. Plug in this expression that you see, 0.01, 0.1, and 1, and notice that you're going to get a very small number after 1 second. You can see that, obviously, because the amplitude decreases. X is decaying. There is no amplitude here, but the value of X decreases as a function of time without oscillation. I've plotted it here too. By the way, notice that the slope here is 0. That's because initial velocity is 0. When you look at these curves, the height, this height is the initial position, and the slope of the curve is actually initial velocity. Now, unfortunately, I forgot to neglected to show you uh, these things when I had earlier opportunity. But when you have x versus time, at time t equal to 0, you get the initial x, x naught, and the slope of that curve is v naught. All right, our last problem is right here. So we have a door which is being stopped by a damper, and you're given some information about this door. First of all, you're told that the mass of the door is 60 kilogram. That entire rectangular thing, that's the door, 60 kilogram. And it has a mass moment of inertia about an axis through its centroid, which is this number that over there. We'll talk about this thing in a minute. There is a torsional spring in this door stopper. Built in it, there is a spring, torsional spring, and there is a torsional damper. And you're told that the torsional spring has this stiffness. Okay, the torsional damper C is usually adjusted. There is a knob here that adjusted so that the C leads to C critical. Okay, so or 0 equal to 1. Be patient, we'll get there. So part A, dimensions of the door are given here. Part A is what should the value of C be so that the system is critically damped? And we come to that A later on. I ran out of time in class. I did a horrible job doing it because I was running out of time, and this I just put the slides on the two slides on the screen. So now we're going to go through this thing in more detail. Don't worry about it. So first thing that you realize is that the mother of all equation, because this is a rotational problem, becomes acceleration. But what acceleration? Angular acceleration, velocity, angular velocity, and there is the position, which is theta. So before we had m x double dot plus c x dot plus k x. Now, instead of x, we have theta, and instead of mass, we have mass moment of inertia about the axis of rotation, okay? And there's a torsional spring in there, and there's a torsional spring in there. That's why I put T's here to remind you that these are torsional. So as far as I goes, it's the mass moment of inertia about the axis of rotation. We are told what the mass moment of inertia about the vertical axis is, but we use the parallaxis theorem, m times distance squared to get IA. And this thing that you see here is the resistive torsional force or resisting torque, resistant torque due to the presence of the damper. This is the resistive force or moment due to the presence of the torsional spring. This is the counterpart of the translational motion, which was mx double dot plus cx dot plus kx. Let's show a few more things here. So these are the kind of things that you did in your dynamics class or machine dynamics class. So basically you have the door view from the top. This is view from the top. So all you see is a rectangle like this. When you look at this thing from the top, this is the axis of rotation. There's the axis of rotation. There's a spring in there and there's a damper in this box. That gives you a moment due to the damper and a moment, resisting moment due to the spring. Okay? And the thing that we solve for is the opening of the door in terms of this angle theta. We don't have a translation here because this is all stuck to the wall, right? Right? It doesn't go anywhere, it just rotates. Now, the axis of rotation that you see here is this white line over there, and the door is represented by these rectangles. The dimensions are given here as 1 meter wide and 2 meters high. And let me also remind you again what the damper, torsional damper does. It resists the opening of the door. Actually, in terms of the velocity of it, it's going to be very hard to open this door very quickly. Okay, that's what it means. Very quickly means high theta dot. And that's the counterpart of what we already know about linear translational dampers. Okay, translational dampers. Okay. Now, the I that you were given was about the I, the line through the centroid here. So if you want to use the parallaxis theorem, you're going to get an I about the axis of rotation. Okay, now, because we are told that this is critically damped, okay, we know that psi is equal to 1, therefore the value of C and C critical are the same. This we know that. So if you, I'm trying to justify where that equation comes from, the one that I just showed you a minute ago. So basically, you write the equation of Newton's second law, which is the sum of all the moment about the axis of rotation equal to I about the axis of rotation times angular acceleration. This is the stuff that you use in machine dynamics and dynamics. And this part of it is because I'm using the parallaxis theorem in order to get the value of I about the axis of rotation itself. Let's do that. So this was given to you. M is the mass of the door, which was 50 kilogram, times the distance between these two parallel lines, okay? That's what parallaxis theorem is. And if this door is 1 meter wide, this is 0.5 meter. So we have D equal to 0.5 and then square it, and we get this number. Now, you plug these things into that equation, you get that. The mother of all equation for rotational motion in this particular problem becomes like that. And the standard form of this is when you divide by the mass, there's no mass here, there's IA, mass moment of inertia, you divide it and you write it in terms of two parameters, psi and natural frequency, omega n. And let me remind you that when you take this thing and divide it by IA, this is going to be omega n squared. So omega n is instead of mass or instead of stiffness, K over m is K over I now, okay, K over I. Torsional stiffness over mass moment of inertia about the axis A, which plays the role of the mass in rotational motion. And of course, again, say zeta is C over C critical, and the same kind of expression that we had before, except that before, C critical was 2 square root of, for example, m times k. And this is rotational motion. Instead of m, you have IA, and instead of k, you have k torsional. Or you can write it like that. It used to be 2m omega n. Now it's going to be 2I omega n. Okay? Choice is yours. So once again, we are told that zeta is equal to 1. So first we calculate the natural frequency. It's going to be stiffness over mass, or torsional stiffness over mass moment of inertia. This was given to us. This we just calculated using Parallaxis Theorem, and natural frequency becomes 1.12. Remember, radians per second. Now, for critical damping, we calculate omega n because I plan to use this formula, this version of the formula. So zeta equal to C over 2I omega n. Okay, but critical damping, zeta is 1. This stuff we know, the denominator we know, we calculate CT, and that's what we were asked. We were asked to calculate. Okay. Now, this is part A of this problem. Part B, let's see what it says. It says, all right, suppose that the door, just hypothetically, suppose that the door is closed, in the closed position, and somebody comes and pushes this door really hard. Obviously, the door will open. Now, really hard means that the impulse that you put on it to open the door is very high. That means the velocity that you give the door is very hard. That's what I mean by very hard. You give it a very large velocity. Obviously, the door will open. And the bigger velocity you give it initially, the more the door is going to open. And then, of course, closes, reducing the amplitude. If you give it a very small velocity, it will open, but it will not open that much. So the question is, what velocity should I give it so that the door opens and opens so that it reaches a maximum value of 70 degrees. It opens by 70 degrees. Because maybe I want somebody to jump through it. My friend who's next to me jumped through the door. And okay, good. So let's repeat this. Initial velocity we don't know. We are supposed to find it. Okay? And we know that it's a critically damped situation. So for critical damping, by the way, this is the expression that we have. Remember, for critical damping, the formula was like that. And A1 and A2 depended on the initial position, which in this case, by the way, is 0. This, I believe it came out to be x naught, but for us, it will be theta naught, which is to 0. Because there is no x for us. For us, it's only angle. Okay, and this thing, we got the formula for it. Okay, but remember, in that formula, that x naught that you see there is actually theta naught. Okay, so we'll get there. So reminder. So initially, when time is 0, the door was closed, so theta dot is 0. That means that A1 is 0. In this expression, it's that t equal to 0, you get A1 equal to 0. The question is, what should theta naught be, theta naught dot be, so that the maximum value for theta that's coming from here is 70 degrees. Okay. So the first thing I'm going to do is, because there is a theta dot involved here, and I don't know what it is, I'm going to differentiate the expression that you see on the top. Now, this discussion is what I quickly went through in just 1 minute. And that's why I told in the class that I'm going to make a supplemental video for it. But everything is going to go into this one lecture. Okay. Therefore, I'm spending a lot of time on this last problem. I spent only 2-3 minutes in the class, but that's not good enough. Okay. So we differentiate this expression theta, and we get this. Okay, remember, we already know A1 is 0, so you can drop this A1 here. This A1 is 0, we already know that. So basically, theta is A2 times t times this exponential. So I differentiate it. Okay. Now, if you set t equal to 0, the left side will be a velocity, right? Initial velocity. If I set t equal to 0, this left side will be the initial velocity that I don't know. I'm trying to find. Okay. Now, if you set t equal to 0, that term goes away, and this term becomes a2. So basically, a2 becomes the thing that we don't know and we want to find. So putting all of these things together, that equation that you see up there on the top right corner is actually this, except that I don't know what theta theta not dot is because I'm trying to find it. I want to do that. I want to find this value so that when I plot theta, it goes all the way to 70 degrees, of course, in radians, converted to radians, and then, of course, beyond that, it's going to drop. You know that the theta will drop, but the biggest value in the graph that I have, I want it to be 70 degrees in radians. Okay, so there are different ways of doing it. Here is how I have arranged it. First of all, I want to find the maximum value of theta. I want that maximum to be 70 degrees, okay? So how do you find the maximum of a function? Well, hopefully you remember your calculus. You differentiate it with respect to time and equal to 0. This is how you find the maximum value of the function that depends on t. Derivative with respect to time equal to 0. Let's do it here in detail. Here's the expression. Of course, I don't know theta dot not. I don't know. I'm trying to find this. So we set it equal to 0. You get this expression. Remember, I calculated derivative for you, right? Let's go back here. Right there. You differentiate this. You differentiate this expression. You get that. Okay, remember, theta dot 0 is a constant. We don't know that. So you plugged it in, and notice that there is a common term, e to the minus exponential, e to the minus omega and t. This cancels. You can divide through. You can divide through. It'll disappear. And you can actually solve for t. It will tell you that the maximum is reached when the time is 1 over omega n. So I know omega n. I know exactly when the maximum is reached. So I plug it in. Let me take this value of t and plug it in there to simplify my job. So what you do is you're going to get the maximum value of theta. When you plug in this t and plug it in there, you get the maximum theta. And there we are. Maximum theta equal to, this number stands. T, we just said, is 1 over omega n. E to the minus omega n. And t, we just said, again, is 1 over omega n. Notice that these omega n's cancel. We get minus 1. Of course, we know what omega n is. And we want theta max to be 70 degrees. 70 degrees converted in radian, so multiply by 2 pi and divided by 360. This is 70 degrees in radians. We don't know theta dot not. I know what omega n is. Just plug it in, and this is e to the minus 1. Put in your calculator, and you're going to get the maximum, the initial velocity that you have to give the door is 3.75 radians per second. If you give it that initial velocity, of course, angular velocity, the door will open and will open 70 degrees, and then the maximum 70 degrees, so your friend can jump through the door, and then it'll start closing because of the damping. And of course, there's critical damping here, and you have achieved your objective. So this wraps up the lecture 3 for January, today is 12, January 12 completely. There is no need to do a supplemental because the purpose of supplemental lecture was to uh, uh, spend maybe more time on that last 2, 3 slides, but everything is not in the same lecture here. I will try. These issues may persist even later on for other lectures. So, and if that happens to be the case, and if I have the time, I will actually uh, do the video for you, basically spending another 1 hour and 20 minutes trying to reproduce the lecture because I can easily record it on my computer when I'm not hooked up to that projector. The class projector is somehow interfering with all the stuff. So anyway, good luck. I'll see you later this afternoon for the tutorial.